we know that the gradient of the function that we've generated to represent a surface is normal to the tangent plane on the surface at a given point. So if I have a surface and I have a tangent plane, a plane that's tangent to the surface, the gradient of that surface function is normal to it. So we can use that fact to generate symmetric equations of the normal line. If you remember, the way that you could do symmetric equations of a line in space that went through a point is you would say x minus, so you'd have the point was at x0, y0, z0, and you'd have these numbers here. And if you recall, the numbers on bottom for the symmetric equations were the direction numbers of that vector. So if we had some sort of line that was in the direction of a vector through a point, you could find symmetric equations. Well, in this particular case, we're in the direction of the normal line, so we can use these partial derivatives to generate those direction numbers and generate symmetric equations. You could also do parametric equations here. That wouldn't be a problem at all, but it's not really what we're doing right now in terms of developing these functions. So let's do an example. We have this equation. This is an equation of a sphere, right? A sphere of radius 3, specifically the shell of a sphere of radius 3. And we have some point, so it's 1, 2, 2. So if I have, x, y, z, it's a little bit, a little bit forward, a little bit over, and a little bit up. So your tangent plane is going to look like this. You're expecting your normal line to go out, kind of coming at you. So to find the symmetric equations, it looks like we need the point, which we have, and it looks like we need the value of the gradient here. Well, that's kind of neat because we need all of this information to get the equation of the tangent plane anyway. So the exact information you need here is the information to get one, you use the same information to get the other. So let's do it. So the function, we have to technically get everything on one side here. And the reason I say technically is because even if we didn't move the 9, the partial derivatives are it would take care of that. So realistically, you don't have to, but from a technical standpoint, from like a rigorous standpoint, you're supposed to. So if we get the gradient, simple partial derivatives, partial with respect to x, partial with respect to y, partial with respect to z. They're not multiplied together, everything else comes out super clean. So the partial, so I want to write something before I go any further. Remember that the equation of the tangent plane is if you look at this equation, you look at these, what you find is you have x minus x0, y minus y0, and z minus z0, and you have partial with respect to x, partial with respect to y, partial with respect to z. You have literally the exact same components. It's just for this one, they're equal to each other and you're dividing, and this one you're adding together and equaling 0 and multiplying. So from a practical standpoint, you have to do the same amount of work to get these answers. That's kind of convenient. So in this particular case, we would have, let's get the partial at the actual point. So let's just fill it in. 1, 2, 2, 2i plus 4j plus 4k. Okay? Then we would do the equation of the tangent plane here is 2x minus 1 plus 4, y minus 2 plus 4, z minus 2 equals 0. We could do some math here and get 2x plus 4y plus 4z. So negative 2, negative 10, negative 18, so that equals 18. And then if it were me, I would divide it and do x plus 2y plus 2z equals 9. You don't have to do that. Again, I'm fine with it here. And sometimes it's actually easier to leave it like this because you can go straight from this to that one. So this is my plane. And that's my line. And it's really just that simple, just same old stuff.